Hey geometers, Mrs. Raff here. In this video, we're going to be looking at the first couple sections of Chapter 8. These are some of my favorite lessons. We're going to be studying polygons and their angle relationships within them. Before we get into that too deep, let's take a look at some basic definitions. A polygon is defined as a two-dimensional closed figure made up of straight line segments that are connected end to end. These segments may not cross at any other points. So what that means is these two are examples of non-polygons. It has a curved side here, and then these sides here intersect not only this top and bottom segment, but the other segment on the side. So this example here is also not a polygon. More details on our definition of polygon is referred to as a regular polygon if it is equilateral and equiangular, meaning all the sides have the same length and all the angles have the equal measure. There are two types of polygons. Polygons can either be convex or non-convex, and you can look at the diagram to see examples of each. In some texts, non-convex polygons are called concave. The definition is given there, the formal definition, but I can also look at, with a non-convex polygon, if I draw a line on all the sides of the polygon, at least one line will cut through the polygon. It's another way I can tell if a polygon is convex or not. In a convex polygon, when I trace every line, none of the lines go through the interior of the shape. And lastly, take a minute and familiarize yourself with this chart here. Polygons are named by the number of sides that they have, and the most common ones are listed here. A dodecagon is fairly common in our curriculum, and that has 12 sides. Otherwise, anything bigger than that, we just name by the number of sides. So, example, if it had 14 sides, I would reference it in the future as a 14gon. So let's dive in. In previous chapters, you've studied triangles and quadrilaterals, but in this chapter, you will broaden your focus to include all polygons, and we'll study what triangles can tell us about shapes with 5, 8, or even 100 sides. By the end of this lesson, we should be able to answer the questions: how can I use the number of sides of a regular polygon to find out the measure of the central angle, and what type of triangle is needed to form a regular polygon? So let's look at Inez here. Inez loves pinwheels. One day in class, she noticed that if she put 3 congruent triangles together, so the corresponding angles are next to each other, she could make a shape that looked like a pinwheel. Can you determine any of her angles? Well, if I look closely at those 3 angles in the middle, I realize that they make up that central 360 degrees. And because those triangles were congruent, I know they must be equal. So each angle there must be 120 degrees. I do not know any of these other angles in her triangles. So I don't know any of the other angles in her polygon. And then it says the overall shape or outline of Inez's pinwheel is shown at right. How many sides does it have? So I'm going to go through and count them. And I learned that this shape has 6 sides. I can also see that this shape is non-convex. And I want you to tell me, what is the name of this 6-sided shape? When we're in person, we do this really cool investigation where we go through the different triangles and we try to make a pinwheel or a polygon. I've kind of laid out some of them here for you. As you can see, this shape is made up of 8 different triangles. So I would know that angle A would have to be 360 divided by 8, or 45 degrees. And while I don't have these triangles laid out just exact, or just so, you can see that this would not be a regular polygon because it has different side lengths here than it does here. These side lengths are either this little section, the difference of the length, or this side here. So this would not be a regular polygon. This would be classified as a pinwheel. Now this is an example of a regular polygon. When I look at this, I have 12 triangles that made up this shape, so I can figure out that angle E would be 360 divided by 12, or 30 degrees. And I also see that all of these angles are the same because they would be D plus F, and all of these lengths are the same because the vertices of the shape meet where the 2 triangles meet. Because I have equal sides and equal angles, I know that this is a regular polygon, and this would be a dodecagon because it has 12 sides. Now looking at the triangle that made this regular polygon, It's important to note that this triangle is isosceles. It creates a regular polygon because these sides match up perfectly, and I have 12 isosceles triangles here. When I look at this first type of triangle that just made the pinwheel, not the perfect regular polygon, these lengths are not the same, which is why it did not make that regular polygon. If I'm going to have triangles make a regular polygon, they have to be isosceles. And it's important to note that every isosceles triangle will not create a regular polygon. Isosceles triangles will only create a regular polygon if that central angle that we're looking at, if 360 is divisible by that angle measure. In this case, it goes in there 12 times, so that's why I know my polygon has 12 sides, because it will use 12 of those triangles to make that polygon. Jasmine wants to create a pinwheel with equilateral triangles. Equilateral triangles are triangles I know that all the sides are the same, therefore the angles are all the same as well. How many triangles will she need? Take a minute and answer the question, how many sides would the polygon created by each triangle have? Now we're going to take a little bit of time and expand our knowledge a little bit more about the interior angles of a polygon. It says, in an earlier chapter, you discovered that the sum of the interior angles of a triangle is always 180 degrees. But what about other polygons, such as hexagons or decagons? What about the sum of their interior angles? Do you think it matters if the polygon is convex or not? Consider these questions today as you investigate the angles of a polygon. So we're going to use what we know about triangles to figure out the sum of the interior angles of different shapes. We're going to start with this regular pentagon. It encourages you to use the fact that the triangles add up to 180. So I'm going to look at this pentagon and I'm going to split it into 3 triangles here. I know this is 180 degrees for each triangle. So I'm going to say this pentagon has a sum of 540 degrees. Now there are certainly other ways that you could subdivide this pentagon into triangles. This is the method that I prefer, so that's what I'm going to go with as we create these. We're going to focus on other polygons here and just kind of go through and see what we can do. So this one makes 2 triangles. So I'm going to fill in this table and I'm going to subdivide these as I go. You can certainly follow along with me. So as I look at this completed sheet, I notice that every shape I have, I always have 2 less triangles. So for example, for a 5-sided shape, I have 3 triangles. For an 8-sided shape, I had 6 triangles. For a 12-sided shape, I had 10 triangles. For a 10-sided shape, I had 8 triangles. So I was always taking the number of triangles I had times 180 to get the total number of degrees. But if I look even more closely, the number of triangles is always 2 less than the number of sides. So if I were to have a polygon with n sides, I would have n minus 2 triangles, and I would multiply that by 180 degrees to get the total number of degrees inside the polygon. I want you to circle this, star this, highlight this, keep this formula handy. We will use this many times throughout this unit. A couple other points to consider. Does the sum depend on whether the polygon is convex? Test this by drawing a few non-convex polygons like this one. I'll test it for this one. So this is a 4-sided figure. And based on my table, it should have 360 degrees because 2 times 180. And if I look at this, I can split it into 2 triangles, so it still works for this figure. What about this 5-sided figure? It is non-convex. So I would know using the formula that it would have n minus 2 times 180 degrees. Well, if n is 5, that'd be 3 times 180 degrees, or 540 degrees. I can subdivide it into 1, 2, 3 triangles. So I would agree that even though it is non-convex, it would still have 540 degrees that make up the pentagon. Then I'm asked, what about a really large polygon? What about a polygon with 100 sides? Find the sum of the interior angles there. I'm going to use my formula and just plug in 100 for the n. That means I could have 98 triangles inside that shape. I would not want to draw that. But if each of those has 180 degrees, the sum of the interior angles would be 17,640 degrees for that 100-sided figure. Lastly, I want you to use what you know about the sum of the angles of a heptagon to solve for x. Since I know the sum of the angles in a heptagon is 900 degrees, I'm going to go through and write an equation and set it equal to 900 degrees. Writing my equation and combining like terms, I have 3x's, and then adding up the highlighted numbers gives me 495. Together, that 3x plus 495 degrees has to equal 900 degrees, so I can go ahead and solve this equation and get my answer of x equal to 135 degrees. So that's a wrap. What you need to know is the sum of the interior angles in a polygon, whether it is regular or not, whether it is convex or not, is given by the formula n minus 2 times 180, where n is the number of sides of the polygon.